Hi friends, welcome to my channel. Before going to the video, those who are not subscribed our channel, subscribe it and also click the bell button. We are going to see about network elements. First, what is a network? A network is the interconnection of two or more elements or components. If the network contains at least one closed path, then it is called an electrical circuit. Every circuit is a network, but all networks are not circuits. What are network elements? These are the components of the network or elements of the network are called network elements. Examples: resistors, capacitors, inductors, voltage source, current source, etc. The elements or components present in an electrical circuit can be connected either in series or parallel or combination of both. Next, let us see the classification of network elements. Based on power delivering ability, these network elements are classified as active and passive elements. Next, based on their characteristic to obey the linearity property, they are classified as linear and non-linear elements. Based on the direction of current flow in the elements, they are classified as unilateral and bilateral elements. Based on whether they are physically separable or not, they are classified as lumped and distributed elements. First, we will see what are active elements. These are elements which can deliver power to other elements in the network or electric circuit. They sometimes can also absorb the power from other elements. Example: voltage sources and current sources. Next, passive elements. These are the elements which absorb power from active elements, or sometimes they dissipate power in the electric circuit, are called passive elements. They can't deliver the power. Example: resistors, inductors and capacitors. Next, linear elements. These are the elements which show a linear relationship between voltage and current. That is, they have the same slope from top to bottom. Example: resistors, inductors and capacitors. Next, non-linear elements. These are the elements which do not show a linear relationship between voltage and current. They do not have the same slope from top to bottom. Example: voltage sources and current sources. Next, unilateral elements. These are the elements that allow the current in only one direction. They do not offer the same impedance in both the directions of current flow. Example: diodes and transistors. Next, bilateral elements. These are the elements that allow the current in both the directions of current flow. They offer the same impedance in both the directions. Example: resistors, inductors and capacitors. Next, lumped elements. These are the elements that are physically separable from the network. Example: resistors, inductors and capacitors. They are not distributed in the network. Next, distributed elements. These are the elements that are distributed in the electrical network and they cannot be physically separated from the network. Example: resistors and inductance and capacitance in transmission lines. They are distributed in the transmission line. Next, let us see how to identify the nature of network elements from their VI characteristics. For that, you have to remember these points. That is, first, if the VI characteristics of a network element is a straight line passing through the origin, then it is a linear element. Otherwise, it is a non-linear element. If the VI characteristic of a network element offer positive impedance, that is nothing but voltage by current value, then it is passive. Otherwise, it is an active element. If the VI characteristic of a network element offer the same impedance value, in both the direction, then it is bilateral element, otherwise it is a unilateral element. Let us understand this by using examples. First example, if you see the VI characteristics, it is a straight line passing through the origin. So it is a linear element. Next, the impedance, that is voltage by current, is positive in both the direction, that is in first quadrant and also in third quadrant. So it is a passive element, and also it offers the same impedance value in both the direction, that is first quadrant, also in third quadrant. So it is a bilateral element. If you see the next example, here the VI characteristics is not a straight line, and also the slope is not same throughout the graph. So it is a non-linear element, and its V by I ratio is positive. So it is a passive element, but the V by I ratio is not same in both the directions. So it is a unilateral element. If you see the example 3, the VI characteristics, it is a straight line passing through the origin, and also it has the constant slope throughout. So it is a linear element, but the V by I ratio, it is not positive. So it is an active element, and the V by I ratio, that is the impedance, is same in both the directions. So also that is in second and fourth quadrant. So it is a bilateral element. If you see the fourth example, the VI characteristic is not a straight line, and also it doesn't have the constant slope. So it is a non-linear characteristic, and also the V by I ratio is not positive, that is the impedance is negative. If you see the first quadrant, it is positive, but if you see the second quadrant, it is negative. So it is an active element, and also it doesn't offer the same impedance in both the directions. So it is a unilateral element. For bilateral, it should offer the same impedance in first quadrant and in third quadrant, or in second quadrant and in fourth quadrant. If you see the example 5, the VI characteristics is not a straight line passing through the origin, and also it doesn't have the same slope throughout. So it is a non-linear element. It has the positive impedance value throughout the graph, so it is a passive element, and also it offers the same impedance value in both the directions, in positive as well as negative direction, that is in first quadrant, also in third quadrant. So it is a bilateral element. If you see the example 6, the VI characteristics is not straight line passing to the origin. So, and also it doesn't have the constant slope throughout. So it is a non-linear element, and also it offers the positive impedance value in first quadrant as well as in third quadrant. So it is a passive element, but it doesn't offer the same impedance value. If you see, the curve doesn't, even if it resembles the same, but it is not the same in both the direction, because here the turning point is at 3 and in downward direction it is at -5. So it is a unilateral element. So you should also see the points. Just by seeing the figure you can't tell it is whether bilateral or unilateral. You should see the VI point in either directions. Next is the classification of voltage and current sources. These are the active elements, and they can be classified as independent sources and dependent sources. Under independent sources, we have ideal voltage source, ideal current source, practical voltage source, practical current source. And under dependent sources, we have voltage dependent voltage source, current dependent voltage source, voltage dependent current source, current dependent current source. Next we will see the ideal voltage source. It is represented as a circle inside which we have plus and minus sign. Ideal voltage source doesn't have any internal impedance. It provides constant voltage. Its voltage is independent of the current flowing through it. So it is an independent voltage source. Its VA characteristics is a straight line with a constant value of Vs. The ideal voltage source is a theoretical one, it is not practically possible. If you see the practical voltage source, it has an internal impedance or internal resistance. This we are assuming as Rs. In practical voltage source, the voltage across the output terminals is Vx, that is source voltage, minus current into resistance value, which is the drop across the resistance. If you see the VA characteristics of practical voltage source, it is deviated from the straight line, that is the ideal characteristics. This deviation is due to the voltage drop across the resistance Rs, that is I into Rs. This drop is the reason for voltage deviation. Next is ideal current source. This current source produces a constant current, and this current is independent of the voltage across its terminals. This ideal current source will not have any internal impedance or resistance. So this ideal current source is an independent source. If you see the VA characteristics of ideal current source, it is a straight line with a constant value of Is. Ideal current source is a theoretical one. It is practically not possible. Next is practical current source. If you see the practical current source, it has a resistor in parallel with the current source. The current at the output terminals will be the source current minus current through resistor, which is V by Rs. If you see the VA characteristics of practical current source, it is deviated from the ideal characteristics, and this deviation is due to the current through the resistor, that is V by Rs. Suppose if an ideal voltage source and an ideal current source are connected in parallel, it is equal to the ideal voltage source. Similarly, if an ideal voltage source and current source are connected in series, it is equal to ideal current source. And you should remember one thing, that is for ideal voltage source, internal resistance is equal to 0 ohm. Similarly, for ideal current source, internal resistance is equal to infinity ohms. For ideal voltmeter, that is voltmeter is an instrument to measure voltage, the internal resistance is equal to infinity ohm. Similarly, for ideal ammeter, the internal resistance is equal to 0 ohm. Next, dependent sources. In these sources, the current or voltage is dependent on either our current or voltage at the terminals. The dependent sources are represented by diamond shape, and for voltage source we have plus and minus side inside the shape, and for current source we have an arrow inside the diamond shape. First is the current dependent voltage source. Since it is the voltage source, inside the diamond shape plus and minus signs are represented, and it is current dependent. So A is a constant value and Ix is the current. So this voltage value is dependent on another current Ix. Similarly, if you see the current dependent current source, since it is a current source, it has an arrow inside the diamond shape and it is dependent on another current Ix. A is a constant value. If you see the voltage dependent voltage source, it has a plus and minus sign inside the diamond shape and its value is dependent on some other voltage Vx. So, and its value is A into Vx. A is a constant value. Similarly, voltage dependent current source. Since it is a current source, it has an arrow inside the diamond shape and it is dependent on some other voltage Vx. So its value will be current I is equal to A into Vx. A is any constant. Next is source transformation. The voltage and current sources can be converted from one source to another based on the requirement while solving the network problems. This technique is called source transformation. The transformation of practical voltage source into a practical current source is shown in the figure. Here the practical voltage source consists of a voltage source in series with resistor. This can be converted into a practical current source as shown in the figure, which consists of current source in parallel with resistor, and the value of this current source is equal to Vs by Rs. Similarly, the practical current source can be converted into practical voltage source as shown in the figure. Here the practical current source consists of a current source in parallel with the resistor Rs. This can be converted to practical voltage source which has voltage source Vs in series with the resistor Rs. The value of Vs is equal to Is into Rs. Next, we will see about the passive components. First, resistor. Resistor is a passive element that opposes or restricts the flow of electric current. It is denoted as R. It is represented by as shown in the figure. If you see, the voltage across the resistor is given by Ohm's law as V is equal to I into R. I is the current through the resistor, and current through the resistor I is equal to V by R. The power dissipated in the resistor is P is equal to V square by R. The resistor dissipates power in the form of heat. Suppose if two resistors are connected in series, then their equivalent resistance is R1 plus R2. The voltage across resistance R1 can be calculated by using the formula VR1 is equal to total voltage into resistor R1 value divided by R1 plus R2. If n resistors of same value R are connected in series, then their equivalent resistance is equal to N into R. Suppose if resistors are connected in parallel, then their equivalent resistance will be 1 by R equivalent is equal to 1 by R1 plus 1 by R2. Current through resistor R1 is equal to total current I into resistance R2 divided by R1 plus R2. Suppose if n resistors of same value R are connected in parallel, then their equivalent resistance is equal to R divided by N. Next is inductor. Inductor is also called as coil or choke or reactor. It is a passive two-terminal electrical component or element that stores energy in a magnetic field when electric current flows through it. And one more thing, inductor opposes sudden change in current. It is denoted as L. It is represented by as shown in the figure. Voltage across the inductor is given by V is equal to L into di by dt. Current through the inductor is given by I is equal to 1 by L integral of V into dt. The energy stored in the inductor is equal to 1 by 2 Li square. Here L into I is equal to psi is the magnetic flux produced when electric current flows through the inductor. Next, inductors in series. If suppose inductors are connected in series, their equivalent inductance is equal to sum of two inductance. That is, L equivalent is equal to L1 plus L2. Suppose if n inductors of same value L are connected in series, then their equivalent inductance is equal to N into L. Similarly, If inductors are connected in parallel, then their equivalent inductance will be reciprocal of the inductors. That is 1 by L equivalent is equal to 1 by L1 plus 1 by L2. Suppose if n inductors of same value L are connected in parallel, then their equivalent inductance is equal to L by N. Next is the capacitor. Capacitor is also a passive two-terminal electrical element or component that stores energy in an electric field when electric current flows through it. This capacitor, it opposes sudden change in voltage. It is denoted as C. It is represented by as shown in the figure. The voltage across the capacitor is V is equal to 1 by C integral of I into dt. Here I is the current which is given by I is equal to C into dV by dt. Energy stored in the capacitor in an electric field is equal to 1 by 2 C V square. Here C into V is equal to Q is the charge stored on the capacitor when electric current flows through it. Next is the capacitors in series. Suppose capacitors are connected in series, then their equivalent capacitance will be reciprocal of the two capacitors. That is 1 by C equivalent is equal to 1 by C1 plus 1 by C2. Suppose if n capacitors of same value C are connected in series, then their equivalent capacitance is C equivalent is equal to C by N. Suppose if capacitors are connected in parallel, then their equivalent capacitance will be C equivalent is equal to C1 plus C2. That is sum of the two capacitors. If n capacitors of same value C are connected in parallel, then their equivalent capacitance will be C equivalent is equal to N into C. Thanks for watching the video. For more videos, don't forget to subscribe our channel.